quelques mots. Alors, tout d'abord, ben, Olivier est directeur de recherche au CNRS et puis il est directeur aussi du laboratoire Gulliver à l'ESPCI. Alors, sa recherche de prédilection sont les systèmes hors équilibre. Donc, il en a étudié de nombreux. Il s'est d'abord intéressé un peu à la transition vers la turbulence dans ses jeunes années, jeunes carrières, plutôt au moment de ta thèse et peut-être un peu après au Sébastien Saclay. Et puis après, tu t'es intéressé pas mal au milieu granulaire, c'est là que j'ai eu l'occasion de te côtoyer, au système vitreux, au mélange chaotique et plus récemment à la matière active. Donc, il nous présentera, Olivier, un peu voilà, ce qu'on appelle matière active, mais bon, c'est des systèmes composés de particules, en général macroscopiques, et qui sont autopropulsés. Ça s'appelle de la matière inerte ou vivante. Voilà, et on peut assister quand des systèmes, voilà, euh, ces systèmes, ces matières actives, on peut voilà, découvrir des systèmes un peu, voilà, des comportements un peu fascinants. Donc, je vais laisser la parole à Olivier. Je le préviendrai au bout de 30 minutes pour lui dire de conclure dans les 5 minutes qui suivent. Et de même pour les questions, donc je demanderai voilà, aux auditeurs de m'envoyer leurs questions par chat privé et que je retransmettrai à Olivier. Voilà. Et je laisse la parole à Olivier pour sa présentation. Donc, si tu voilà,
Oui,
partager ton écran.
Oui. Alors, hop, ok, fait.
C'est parfait.
Alors, là, je suis pas en mode présentateur, si, non. Euh, Affichage,
Tu peux mettre en mode
mode présentateur.
spectateur.
Là, c'est bon, vous voyez juste la slide?
On voit les deux, en fait, la slide suivante, en fait, on voit les
Ah
deux.
oui, non, alors c'est pas ça que je veux. C'est affichage plutôt.
Diaporama, voilà.
Voilà,
Parfait, c'est parfait.
très bien. À un moment, il faut que moi, je ne me vois pas trop. Voilà, parfait. Ok. Eh bien alors, bonjour à tous et merci aux organisateurs de m'avoir donné l'occasion de présenter un peu des travaux plus anciens et très récents sur ce sujet de matière active. Et je vais passer à l'anglais, évidemment, pour la présentation. So what I would like to discuss today is these strange materials that we call active matter, and I will come to a precise definition of it. And I will discuss a number of properties that have been studied in the past 25 years and that concern the active liquids. And very recently, there's been more interest into active solids, and this is the very recent work that I will come to, let's say, around the half of the presentation. And so we will see that in active liquids, and this is what has driven the field from the very beginning, spontaneous collective motion can emerge. And I will show you that in active solids, this collective motion turns into collective actuation of some specific modes of the solid. So the recent work, so I cannot list all the collaborators and students that have participated to all of this work, but at least the recent work, people who were involved in those are Michael Schindler, also from the Gulliver Lab, and Vincent Demery, and Gustavo Düring from Chile, and Corentin Coulet from Amsterdam. And the three students who really worked with me on these topics are Julien Dessaigne, Guillaume Briand, and Paul Bacconi. So, I cannot move from one slide to the next. That's strange. So we have a problem here. I didn't want to move slides. Maybe here. Okay, it's not the most. I'm not sure this will be okay. Okay, we'll see. So, as I promised, let's start with the definition of what active matter is. So, it's some kind of a matter of which the atoms are active units. So, what do we call active units? Active units are particles in some sense that follow a dynamics, and this dynamics is not the standard equilibrium-like dynamics. It must break time reversal symmetry, and it must also break space isotropy. So a typical particle belonging to this class is a particle that will harvest energy from its environment, dissipate some of this energy and produce some work. But on top of that, the particle is not isotropic. It has some specific direction. So a typical example of this is any kind of animal that is performing a motion is belonging to this class of active matter particles. So this is really the basic tool, the basic object. So the idea of talking about active matter is really to have this image in mind. You consider your usual atoms, you want to consider many of them. And instead of these atoms, you consider, for example, animals like birds or robots, or let's say, for example, these grasslands. You can consider that each piece of grass is something that indeed harvests, consumes energies, grows, and then they are coupled together. And as a whole, you would like to study this as a material. So why is active matter interesting for a condensed matter physicist? Well, first of all, it's probably one of the simplest out of equilibrium matter phases that you can study, in the sense that they are intrinsically out of equilibrium because the individual components are already out of equilibrium. So you don't need to drive them with external boundary conditions or gradients. You can really study homogeneous phases, and you can really talk about phases. Like here, this cloud of mosquitoes is really like a gas. This herd of sheep is really like a liquid when it flows through a gate. And when you consider a tissue of cells, you can really think of it as a solid. So, so somehow we are in a context with which we can use the usual words of physics, and these systems offer new physics, really new, in the sense that they are qualitative new phenomena. So in active fluids, for instance, the mechanical pressure is not a state variable, even for non-interacting particles. You can observe a liquid-gas phase separation that takes place in purely repulsive systems, which is impossible at equilibrium. Macroscopic flows can emerge in the absence of external gradients. So you see, these are really qualitative new statements, new physics that call for new explanations. This has been the topic of the past 25 years of research. And as I said, more recently, people have started to look in active solids driven by the motivation of studying tissues, biological tissues. And I will show you today that even in a crystalline structure, you can have spontaneous flows. And this is really uncommon for people of condensed matter. And I think this is why it's interesting. And then I will show you a very recent work about the emergence of spontaneous oscillations that take place collectively in an overdamped linear elastic system. Okay, so does it mean that we need to have mosquitoes, sheep, and cells in our labs to start studying these systems? Well, fortunately not. We can actually engineer active particles and study active matter that is much more comfortable to deal with. So let's start, for example, from our very familiar Brownian motion, where you have detailed balance and the particle is isotropic. Well, you can move from there, from this little colloid typically, to create an active colloid by using phoretic motions. That is, you manage to break the isotropy of the particle by coating it, for example, with some catalyst, and then you have a chemical reaction that will take place specifically on one side of the particle, and then you will have gradients of concentration on the surface of this particle, and because of this, you will have flows that can be actually measured, as you can see on this right picture, and then the particle is moving. So this is one typical example, and many people have studied different versions of this. Another path is to, why is it sometime? Okay, another path is to use more biological objects. You can imagine that you coat a cover slid with molecular motors, here myosin, and then on top of this carpet of molecular motors, you can have an actin filament. And so this active filament will move around in a polar direction. And you will get some kind of what is called a motility assay where these filaments together can create interesting patterns. The path that we followed is a bit different because of my culture. As Alexandre said, I was studying granular materials. And when you study granular materials, because they are big particles by definition, they are not sensitive to Brownian motion. You need to shake them if you want to see something. But there, indeed, there is no detailed balance because these particles are dissipating energy. But these are isotropic particles. So this is not yet active matter. If you want to go to active matter, you must break the isotropy of the particle. And so you can do this with rice. And then you will have nematic active matter, or you can do it with sunflower seeds, for instance, and then you will have polar active matter because there will be a head-tail symmetry that is broken. So these are typically the kind of tools, of course, a little bit more engineered than those ones that we are going to use. So the outline of the talk is that I will first give a brief overview with a focus on collective motion of active fluids. And then I will move to active solids as promised to show you these two really spectacular phenomena that are really new, spontaneous flows taking place in crystalline structure and selective and collective actuation emerging in linear elastic systems. But to do so, I must first introduce our favorite active units, the one that we use in my lab. So one is the X-Bug. It's really a toy. It's really a toy for kids. The energy source is a battery inside the X-Bug, and there is also a mobile phone vibrator inside this little animal. And then the plastic legs that are curved contribute to the propulsion of the little bug. And as you can see in this commercial, these little things start moving. You can put a lot of them together and study their collective motion. And amazingly enough, the promoters of these X-Bugs even have a little feeling of the renormalization group, as you can see here. Okay, so now that you have your little favorite animals, oops, no, we don't want them twice. Sorry. It may be nice to describe them with some equations, and well, you just write down Newton equations. We are in the classical world, so you have one equation for the acceleration that has a propulsion force in the direction of the particle, some damping, and then external forces. And in principle, because now the particle has an orientation, well, this orientation in 2D corresponds to an angle. And so you have 3 degrees of freedom to describe this particle. And so there will be an equation to describe the rotation of this angle. And so there will be some acceleration for the angle. There will be some damping. Potentially there can be external torques. And let's say we can also add some noise on this angle. You could also add noise on the translational degrees of freedom, but it plays no critical roles. Now, it happens that if you do this, you miss one ingredient. And this ingredient, I will illustrate it in this movie here. So I will drag one of these bugs along this square here, and you will look at the motion of the bug. So let's start this. Let's start. Come on. Okay, so you see I'm dragging this, and you can see that what's going on, so I impose the velocity, and what's going on, or the displacement, is that the bug aligns on the direction that I impose. And this is a very specific behavior, and this calls for adding a torque, an active torque, in this equation for the rotation. This is very important. So otherwise, if you don't have this, the first equation will, of course, align the velocity towards the direction of that is imposed by the geometry of the bug, but you would not have the fact that if you impose the displacement, the orientation of the bug rotates towards the velocity or the displacement. And I will call this self-alignment. And this is a property that is common to all active particles that are somewhat walking on the ground. It may not be true for swimmers, but it's true for all walkers. Okay, now the second kind of active particle that I will play with are much smaller. They are like 4 millimeters, and they are little metallic discs. So I will use 2 kinds. One are these isotropic particles, and when you shake them on this kind of shaker there on the left, they perform a motion that is isotropic and very close to the Brownian motion, actually. The one I will focus on are polar particles. You can see it has two different legs. One is a very strong rubber, one is metallic, they have different shapes. And because of this polarity, this geometric polarity that I induce, that I engineer in the particle, when you shake them, they behave as if they had a little engine inside, and they perform a directed random walk. These particles also have this self-alignment property, as you can now see on this movie. So you can see now I'm shaking, the particle is moving more or less in all directions. And now if I push it, you can see from the little black dots that it's typically aligned in the direction of motion, although it's much more noisy than the previous one. So these will be my two favorite players. And now let's move to the three topics. So first, let me rapidly show that mechanical pressure is not a state variable. So mechanical pressure, one easy way to compute it or to measure it is to consider a wall that is defined by a potential. And then you put particles in this box, and there will be some density profile. And at some point, the density will be 0 because you cannot cross the wall. And so the pressure is simply the integral over space of the density times the force that you exert on the wall. That is the derivative of this potential. And you see that for an ideal gas at equilibrium, well, the density we know, it's the probability of presence, and so it's just the Gibbs formula. And so when you inject this in here, well, you realize that you can immediately integrate this and find that the pressure is, well, the ideal gas law with no surprise. I think it's the fastest demonstration of the ideal gas law. But the good thing is that you can apply this procedure in principle for active particles. But of course, for active particles, we don't know what is the density profile because we don't know what is the steady state distribution for such a gas of particles. So let's do some experiments. I will have a chain here. This little chain is on the shaker that I showed you before. And here you have this little disc that can be either the isotropic on the polar disc. And then just by some geometrical construction, measuring the average length of this chain, the radius of this chain, measuring the forces here, you can actually measure the pressure, the mechanical pressure exerted by this disc on the chain. So this is my barometer. And if I use this, I can measure this mechanical pressure that is always well defined for the isotropic particles, but also for the self-propelled one or the active one. Well, in both cases, I find a curve. These curves are different. No, not so much surprise there. Mechanical pressure has no reason not to exist. The surprise comes from the fact that if I do this experiment now, where I equilibrate a system of isotropic disk with a system of active disk, and I run the experiment, well, I can equilibrate mechanical pressure, and I need to have 200 self-propelled particles to equilibrate 627 isotropic particles. But now look what I'm doing. I keep exactly the same number of particles, but I change the chain, and only the chain. And I redo the experiment. And then what you see is that these 200 self-propelled particles are now compressing significantly the 627 isotropic one. And if I want to restore the equilibration, I have to decrease down to 75 the number of self-propelled particles, which means that the mechanical pressure felt by the isotropic particle has changed simply because the chain has changed. And indeed, if we now measure the pressure for the isotropic particle with the two chains, we find the same curve. But if we do the same measurement for the self-propelled particles with the two chains, we find different mechanical pressure. So we conclude from this that this line here is really disturbing. Where can I put it? That there is no equation of state. No, the mechanical pressure is not a bulk variable for this very simple active system. I mean, just disk. I'm not even talking about particles that would have different shapes, etc., etc. So this is the first striking result I wanted to show you. Now let's move to the second one, which concerns the emergence of macroscopic flows in the absence of external gradient, and which is actually the topic that really launched the field of active matter. So The very initial event that launched this field was a paper published in '95 by Tamas Vicek, who introduced a model of point particles that are self-propelled. So you can think, and they move at a given velocity. The speed is fixed in a direction n, which is the polarity. So you can really think of them as spins moving in a continuous space. And they align with their neighbors. They align ferromagnetically. So it's really ferromagnetic spins moving in the continuous space. And there is some noise. And what these authors demonstrated, and later Hugues Châtet and others, is that there is a transition when you reduce the noise or when you increase the packing fraction or the density. There is a transition from a disordered state where all particles are moving in all directions to an ordered state where somewhat the system is magnetized and everything is moving in the same direction. And this transition is a bit peculiar because it is discontinuous. It has it is really a first order transition, and in between these two regimes, these two phases, these two homogeneous phases, there is a phase where you have fast domain growth leading to high density and highly ordered solitary bands propagating in the system. Okay, so this is a model, very, very simplistic and simplified model. Can we reproduce this in experiment? So the first experiment where this kind of collective motion were really demonstrated, using also a little bit the help of in silico experiment, is this system of disk. So if I again take my isotropic disk, but I shake them, well, then what I see is really a nice standard liquid, I would say. It's dense and the particles are moving in all directions, and okay. But if I do the same with the particles that are polar, this is what I see. I see that at least at a certain scale, there are grouped motion where particles move in the same direction. The color codes here for the direction. And we can measure some kind of order parameter for this, which is, let's say, the magnetization of the system. And whether you look at the distributions of this magnetization, or its mean value, or even the spatial correlation or the temporal correlations of this order parameter, there are strong evidence, at least of a crossover towards an ordered phase. Well, of course, the system is a bit small. We have a few thousand particles, and there are boundary conditions that are not periodic. So all this may be influenced by this. But fortunately, we have this model that we know describes quite faithfully this kind of particles. And in this model, we could run simulation of much larger systems with periodic boundary conditions. And there you see that indeed there is really a macroscopic flows here going typically from the left to the right that develops in the system. You can study the phase diagram. There is a first order transition from the disordered to the ordered state. And in the coexistence region, there are these solitary bands that propagate in the system. So with this mix of experiment and numerics, we could demonstrate that in a very simple system of active disk, you can obtain this transition to collective motion. Now, this system is not the only one in which we observed collective motion. There is a system that was invented by Denis Barthelot at SPCI when I moved there in 2011. And the system is very simple. You will have to believe me a little bit, but believe me that if you take isolating particles, colloids, and you put them in a poorly conducting fluids, and you impose a static electric field perpendicular to these two electrodes, then these particles start rolling. Well, they start rotating, and because they lie on the bottom electrode and they rotate, well, they will start rolling at a given speed that is extremely well defined and that can be computed explicitly. This system is amazing because you can, of course, with colloids, you can put millions of them. And we recovered the same transition from a disordered dilute. So here what we change is more the density of particles. And here you have a dilute system of particles that move in all directions. Here you can see, or at least these little arrows show you that all these particles are moving in all directions for larger packing fraction. And in between, I will show you these solitary bands that propagate. And what is important here is to point the fact that the electric field is a static field and is perpendicular to the field of view. So it's just a way to provide energy to these particles, but they move in a direction which is their own. Okay, so, and this is really an amazing realization of the Vitsec scenario. So now, let me move to these active solids. So first, let me show you what happens, which really is mesmerizing. I mean, if we have this disk, it's very easy to compactify them. And you all know, I mean, it's not in this assembly that I will explain that if you compact disk, well, they crystallize. And they crystallize on a triangular lattice. So I can put my little disk in an hexagon that matches the geometry of the triangular lattice. And if I do this for the isotropic disk, I can really create a perfect close packing crystal if I put precisely 1,141 particles in my little hexagon. And I can do the same for this disk, for this polar disk. And then I can shake. And I can remove some particles. So of course, if I do this for the isotropic disk, you remove some particles, well, you create frustration in the system because you cannot have the order. And so you will see defects. And you can see these defects here that develop in the system. And when you remove more particles, well, the defects organize differently. And then when you have removed exactly one layer, then you can again form a perfect crystal because the packing fraction is still far from the melting packing fraction of 0.81 something. Now, if you do the same with the self-propelled particle, well, if you remove the same number, well, here it's very similar. There's not much change. But as soon as you remove enough particles, then the structure of the defect is completely different. And for the number of particles where you would have recovered the crystalline and ordered structure for the isotropic particles, it seems to be a complete mess. Still, the pair correlation function is really that of a crystal. Now let's look at the dynamics, and this is where really it becomes amazing. For this packing fraction here, where I have exactly 1,085 particles, this is what we observe. The crystal is actually flowing. It is melting in the center a little bit. It is compactifying on the outside. And these absolutely close packed crystals are moving. They are translating, and they manage to flow in this spontaneously in this otherwise closed vessel. Now, of course, again, this is an experiment. There could be a bias in the vibration. So again, we performed simulations with our favorite model. This is a simulation that is conducted exactly in the same condition as the experiment, same packing fraction, some noise, etc. And after some transient, you can see that indeed the system organized from these lines of defects and manage to flow. I mean, this is a solid that is flowing. And you can even suppress the noise. And if you suppress the noise, you have a clock. You have a solid clock flowing in the box, I mean, which is very close to close packing. So this is really something that when I saw this, drove me really completely crazy. And then we increase the system size, because of course we know that when you increase system size, especially in 2D, things can become a bit tricky. But the more we increase the system size, the better is the crystalline structure. And when you look at the flow, that is the motion parallel to the wall, well, you can see that close to the wall, it is perfect. It is actually even stronger when the system is larger. And the fraction of the system where it is weaker is actually smaller and smaller when you increase the system size. So we have a bona fide flowing crystalline phase. So of course, liquid crystal is a word that is already used by all of us. So we need to find a new word for that. And I didn't find one better than rheocrystal. If you have some idea, of course, please, you are most welcome. But really, this is an amazing phase of matter. Now, this phase, I mean, must have some elastic properties. I mean, we are in close to close pack in a crystal. These little particles are colliding with some interaction potential, very hard, presumably. And we all know that this leads to some elasticity. So what about doing what we have in our first page of solid state physics? That is, let's take a lattice of elastic springs with the little atoms on the nodes, except that I change the nodes and there are no more atoms. There are these little objects where I have put an X-bug, and the X-bugs can rotate freely. So the spin of the X-bug or the polarity of the X-bug is a free degree of freedom, but the translational degrees of freedom are pinned in the crystalline structure. So there are two ingredients. The X-bugs can exert some force and so extend, of course, the spring. And the ingredient that I already presented you, that is that if I impose a displacement, the X-bug align on the displacement. Now, if I take one of these units and I pin it on one node of a triangular lattice, then it happens that because there are only two ingredients, there is only one control parameter. And this control parameter is the ratio of the length that the active force can elongate a spring. This is just the force divided by the stiffness of the spring, divided by this alignment length here. That is the length on which the displacement that must be imposed on the X-bug to align it with the displacement. And when I increase this, and here I increase it by reducing the stiffness of the spring, by elongating the springs, this is what I observe, is that when this control parameter pi, which describes the ratio of these two lengths is small, well, the thing essentially diffuse. But then when it's large, well, there is some kind of an orbiting periodic solution that the system adopts, and in between it's a bit messy. Okay, but that's one particle physics. So can this happen in a lattice? So we built here a lattice.
Olivier, juste pour te dire, il te reste 5 minutes.
Parfait. So here we have this lattice, a triangular lattice, but it's free to move in space. And so here what I observe is that they manage to align through the elastic coupling and translate. Okay. Then I can actually restore a little bit the rotational symmetry of my lattice by removing the X-bug that is in the center. And then I can stabilize solid body rotation of this system. Well, these two modes are trivial modes of a solid. They are the translational and the solid body rotation of a solid. Any solid wants to do that if you provide it with some energy. Well, it's not completely trivial, but it's okay. Now, what I will do is something a little bit more tricky. I will pin the lattice in the lab by fixing the external boundary. So now there is no more any zero mode in this system. And it's a very stable elastic lattice, very far from isostaticity. I mean, all the modes are perfectly known. And now I increase this control parameter. And what I observe is this. That is when the control parameter is large enough, there is a spontaneous oscillation in phase of the nodes of the lattice. Again, this is a pretty small system. We can use our favorite model. And here we are even going to overdamp the dynamics. And we are going to consider only harmonic elasticity. So there is no nonlinear effect coming from the elasticity. The only nonlinear effect comes from this coupling between the displacement and the orientation of the polarities of the particle. And there again, we reproduce perfectly the experiment. The crystal, the lattice exhibits spontaneous oscillation if the control parameter is high enough. Can we increase system size? Well, yes, we can perform actually very large crystal. And now look at these mesmerizing videos here. When the control parameter is large enough, in a finite fraction, finitely large fraction of the system, you have a spontaneous oscillation of the crystal. So this is really a material. This is a material that is cohesive. And this material is dancing the hula hoop spontaneously. This is something that is really cannot happen, of course, at equilibrium. And I think it's the first time that we have a human-made material that spontaneously presents a dynamical phase. This phase is a chiral phase that breaks the parity symmetry because it selects one orientation of rotation. Of course, if you redo the experiment, it will select randomly one or the other. Okay, so we studied this phase in detail for different lattices. And I will just make a few points. The first point is that the oscillation selects a pair of modes and concentrate most of the energy on one pair of modes. This pair of modes is not always the lowest energy one. It happens that in the, there is a mistake here. It happens that in the hexagon, it is the lowest energy one. But in this lattice here, which is a Kagome lattice, so these two pictures should be inversed, it is actually the fourth and the fifth modes that are excited. And you can see that the lowest energy modes are not excited. So there is a nonlinear, non-trivial selection of the modes on which the energy condensates to produce the oscillations. The second thing is that, as I showed you, if you take a large system, if you have a very large control parameter, all the system is oscillating in phase. But then if you decrease the control parameter, as you could see in the movie, only a fraction at the center of the system is rotating. And there is a discontinuous transition where at some point, suddenly this center here reach an oscillation frequency that continuously reach zero. But this happens where there remains a finite fraction, and then suddenly the system stops and everything is arrested. But this critical fraction is always a finite fraction independently of the size of the system. And whatever the size of the system, the condensation on two modes remains very strong. Typically 70% of the energy is condensated in two modes. So there is a coexistence between the frozen disordered phase and the chiral one when the system is large enough. Okay, so let me conclude here with the following outlook. So active matter physics started with the study of collective motion, and this was inspired by biology and the physics of flocks of birds in 1995. In the past 25 years, active liquids have driven a very intense research, and physicists have designed a large amount of model experimental systems and numerical models that have led to the observation of a bunch of striking and interesting phenomena. And I illustrated two of them: the fact that mechanical pressure is not a bulk state variable, and the fact that collective motion can emerge spontaneously. There are others. On the theoretical side, kinetic and field theories have led to a rather good understanding of these phenomena today. Very recently, the study of biological tissues has driven part of the community towards the study of highly dense systems, which eventually behave as solids rather than liquids. I've shown you that very fascinating phenomena can emerge in solids, maybe even more fascinating than in liquids. But a lot remains to be done to fully understand the physics of active solids. And I believe that tools from condensed matter physics, and maybe even hard condensed matter physics, like symmetries, group theories, and so forth and so on, are likely to become increasingly helpful in this field. So if you are interested, I've put here a few references about what I told you about today. And above all, I want to thank you for your attention, and I'm ready to answer your questions.
Merci Olivier pour cet exposé passionnant. Alors, j'ai eu plusieurs questions qui revenaient sur l'expérience. Beaucoup de personnes ont été intriguées par ton expérience avec la chaîne.
Ouais.
Notamment des questions de Paolo Giancalo, de Thomas Bourdel, Isabelle Canta, qui n'ont pas très bien compris quelles sont les propriétés de la chaîne que tu as modifiée.
Ah, j'ai modifié, donc elle fait exactement la même longueur, mais c'est une chaîne qui contient, donc ce sont des chaînes typiquement comme les chaînes qu'on utilise pour accrocher les bouchons dans les baignoires. Et c'est une chaîne qui contient, qui fait la même longueur, mais qui contient moins d'unités. Donc elle a un design mécanique un peu différent.
Moins d'unités, c'est-à-dire que...
Tu sais, c'est des chaînes avec des petites billes.
Ouais, les petites bits, d'accord.
Et les petites billes sont donc dans la première chaîne, les petites billes sont plus grosses et il y en a moins pour faire la même longueur que l'autre chaîne.
Très bien, bah, je
C'est tout.
pense que ça clarifie.
Donc en fait, elles ont juste des propriétés mécaniques un peu différentes, ces deux chaînes, et ça suffit à faire que la pression mécanique mesurée soit différente.
Alors, très bien, je pense que ça précise les choses. Alors, je me permets, oui, de me poser une question, puisque ça concerne le même système. Donc, pour créer l'anisotropie, là, effectivement, tes particules ont des plots un peu différents. Et qu'est-ce qui crée l'anisotropie? C'est le frottement ou c'est le…
Oui, c'est le frottement et la différence de coefficient de restitution élastique aussi,
D'accord.
entre
Ah oui,
l'avant
alors,
et l'arrière,
oui.
entre l'avant et l'arrière de la particule.
Alors, excuse-moi, pour la question précédente, est-ce que tu pourrais reformuler ta réponse en anglais? Parce que
Oh,
c'est pour
sorry.
Paolo ou Giancarlo.
Sorry,
Voilà.
sorry. So for the chain, so the two chains are almost identical. The only difference is that these chains are composed of beads that are attached together. The only difference is that one chain has slightly larger beads and less of them to make the same length as the other chain where the beads are a bit smaller. So essentially, the two chains have slightly different mechanical properties. And the answer to the second question about the self-propelled disk. So what makes them anisotropic is these two legs here. And it is the friction coefficient, of course, and also the restitution coefficients that are different that makes this anisotropic.
Très bien. Il y a plein d'autres questions. Donc, maybe I switch in English because the question are in English. So there is a question from Guillaume Dumazer. So he said you mentioned that non-isotropic granular particles such as rice may have a collective behavior. Do you know some example in nature or industry where a collective dynamic are visible?
So in nature, I don't know. So experiments have been done with grains of rice. And so what you see there, of course, now there is not one direction for the particle. So it doesn't have a mean velocity. But what you see is that if you are dense enough, you form some kind of a nematic phase. And usually when you are at least on a plane in a nematic phase at equilibrium progressively, so you know that in nematic phases, there are also defects with charges that can be positive or negative. And at equilibrium, if you are, in an infinite plane system, these defects annihilate. In an active system, like vibrated rice grains, the defects never annihilate. You actually permanently create new defects, and the positive defects are embedded with a finite velocity. So there are some specificity of these active nematics. And in nature, they appear when you look at dense assemblies of microtubules, which is the most famous system to use to study active nematics.
So thank you, Olivier. I have another question from Akalin Tashin. I don't know if I pronounce well his name. So you mentioned you have you considered the doping of your hexagonal?
Not yet.
Not yet.
Not yet. Yes. Doping of crystalline phase. So there are many ways of doping. You can imagine to take a purely passive crystal doped, for example, the passive crystal of disks. You could imagine to dope it with active disk. You can do the reverse. You can have an active crystal and dope it with passive disk and see how long the flowing crystal will survive when you increase the fraction of passive disk. You can also indeed dope the X-bug crystal by having different kind of X-bugs with different strengths or different things in the… No, the room is completely open. We have not studied disordered lattice. We have not studied lattice on the verge of collapsing, etc., etc. There are plenty of things to be done there. This is only the first page of the solid state physics books, right?
And maybe a last question, a basic question about the frequency of oscillation in the active matter.
Mm-hmm.
What is the dependence of this oscillation frequency with the parameter of the system?
Okay, so this is a good question. So let me just move to the corresponding slide. So for the, oops, here we are. Okay, so for the one particle system, you can compute it exactly. And the threshold for the setting of the oscillation is given by the lowest eigenfrequency of the dynamical matrix. So when pi is equal to omega square mean, where omega square mean is the minimal eigenvalues of the dynamical matrix, this is the threshold. Then the frequency goes like the square root of 1 minus this threshold. Now, when you move to large system, this is not true anymore. Let me show you the curve. Where is it? It's here. When you move to large system, this frequency here as a function of the control parameter seems to be a non-trivial Power law, closer to 1/3. But it's a mix, the dependence of this is a mix of the fact that the particles that are rotating reduce their frequency, but also the fraction of particle that is rotating is decreasing. So this is actually mixing two effects. So I don't know if this exponent is relevant or if it's the composition of two exponents and we should better look at things separately. This is really under investigation.
Et merci Olivier. Peut-être une dernière question de la part d'Éric Collet. Donc, je vais te la dire en français parce qu'elle est un peu longue. Donc, pour les transitions de phase, il peut y avoir un couplage entre densité, quand c'est totalement symétrique, et les paramètres d'ordre brisant la symétrie. Est-ce qu'on observe ici des corrélations entre densité et mise en ordre? Est-ce que ces deux instabilités peuvent avoir lieu de façon simultanée ou séquentielle en fonction des paramètres de contrôle?
Okay, so let me rephrase in English for the non-French speaker audience. Yeah. So essentially, I showed you transitions where the other parameter has also always something to do with this polarity. So it can be magnetization or something else here for this oscillation. But especially in the liquid case, I mean, the density field is a non-trivial field. It's also a slow mode because of mass conservation. And so it's also another parameter. And so the answer is yes, especially in liquids. The coupling between the magnetization and the density field is responsible, for instance, for unique dispersion relation for sound. And the sound propagation in polar active liquids obey a very anomalous, very similar to liquid helium, actually, second sound propagation. And this is because of this coupling.
Thank you. And maybe a very last question from Arnaud Prigent. What happened is the form of the box is modified from hexagon to octagon, for example?
We have in the disk, in the flowing crystal, or in the so in the
it's not specified, but
didn't specify. So if you so I have movies, but I don't have time to show it here. So if for the flowing crystal, if you take boxes of different size, the system essentially managed to flow by isolating regions that do not flow to restore an hexagonal box. So imagine you do a square, it will draw an hexagon inside the square and isolate the corner of the square, which will essentially not move. If you increase the size of the square like mad in simulations, then what you see is that actually the corners start moving and form little hexagon that isolate smaller corners, etc. So this is for the flowing crystal. For the lattice, well, there we don't really have a size of a box. It's more really the geometry of the lattice that matters. And it's really the group of symmetry of the lattice that is important for the selection of the modes.
Alors, c'était pour le cristal.
OK, so good.
Merci, on va s'arrêter là. Donc, merci encore Olivier pour cet exposé fascinant. Et merci à tous les auditeurs pour leurs questions. Et pour conclure, je laisse la parole à Isabelle Quentin.